Hello. Recently, I was looking at Bernoulli sequence and probability of N, P, and Q, success and failure. I'd like to just do one work through solution and then have a look at the graph of this particular situation. I'm going to look at a question which is from the book that I'm operating. It's on page 602. It's in the book I'm using. It's exercise 14A. And I'm going to be looking at number 8. If the screen can catch up to me, it seems to be lagging. It's not a good sign. Joe knows that each ticket, oh no, that's not the probability I wanted to look at. Suppose that the probability is number 9. Suppose that the probability that a person selected at random is left-handed is 0.2. So let's put P as 0.2, and therefore Q, which is 1 minus P, is 0.8. 11 people are selected, so we told N equals 11. Write down the general rule for the probability distribution of the number of left-handed people. Okay, the probability of the general rule, that's X equals some value, how many people we want. That will be 11CX, P to the power of X, so X successes, and I'm going to put P as 0.2, so because it did ask us to replace P and Q for the general rule, we can use 0.2, X successes, and failures is 11 minus X. Okay, that's the general rule. That was part A. Part B. Use the rule to calculate the probability of selecting exactly 2 left-handers. Okay, we want exactly 2. That is 11C2, 0.2 to the power of 2, and 0.8 to the power of 11 minus 2, which is 9. Now, 11C2, I'm going to also use the rule how to get 11C2 using the rule that NCX, I'll just put the rule here, is n factorial divided by x factorial, and then the difference between n and x, the other number that adds up to x. 0.2 squared and 0.8 to the power of 9. I think I can get this to, let's just use the basic calculator. I'm going to go 11C2 times 0.2 to the power of 2 times 0.8 to the power of 9. And that is approximately 0.295279 ... And so I'll put 0.3 for 0.30 for 2 decimal places. Doesn't matter. Okay, part C, or B part 2. Find the probability of no left-handers. So we want no successes. So that is 11C0. No successes is 0.2 to the power of 0, and 11 failures is 0.8 to the power of 11. So 11C0 is 1, 0.2 to the power of 0 is 1, and 0.8 to the power of 11. And that is approximately 0.8 to the power of 11. 0.085899. So that's say 0.086 to 3 decimal places, depending on how accurate the question wants. At least one left-hander. Okay, part 3. The probability at least 1. Now, at least 1 means 1 minus the probability of none. You see, we're going to use the fact that we could calculate 1 plus 2 plus 3 plus 4 plus all the way up to 11. The only one missing is 0. So if we work out the probability of 0, take it away from 1, and we will have our answer. And we've already worked that out in part B. So at least 1 means 1 minus the probability of none, 0.086, and that is approximately 0.9914 to 3 decimal places. Okay. What I'd like to do using this question is actually look at a graph. Now notice P is 0.2, so we're going to have a lot of low successes and more high successes. So let's find the probability of a success. I'll just sort of raise this up if I can raise this up. Okay. Now I'm going to get a table for 0 successes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 successes. There's no such thing as 12 successes. Okay, now I'll get the graphic calculator for this one. Let's hope I didn't take it downstairs. Oh, there it is. Hang on. Okay, let's go to sequence. Put in the formula, 11 factorial on the numerator, 11 factorial. You have to find that in the symbol. We want x factorial, and 11 minus x factorial. 0.2 to the power of x and 0.8 to the power of 11 minus x. Okay. Let's get our table of values starting at 0, ending at 11. Okay. So by putting this into the calculator, I just used the graph and I just went 11 factorial over 2 factorial. Sorry, not 2 factorial. I want a formula for x. So I used x factorial, 11 minus x factorial. I used that general formula from above and I put it in a graph. And I got the graph. I ticked the box and I pressed the icon which gives me a table. And I got the table which said 0 up to 11. All right. So I'm going to just put those values along here, and I got 0.086. I'll just put 0.086. For 1 is 0.236, 0.236. For 2 is 0.295, 0.295. For 3 is 0.222. For 4 is 0.10111. For 5, it's 0.039. For 6, it's getting ridiculous. 0.00097. For 7 is 0.002. For 8, it's 0.0002. And we're getting almost a chance of we're getting into 1 in 10,000 here, 0.00002. Okay, you can see we're getting very small. Okay. Now the graph of this, I just want to show you for exercise 14b. The highest probability here is about 0.3. So if I get a vertical axis, let's try and draw this on the graph. And I'll go across 11. Okay, let's go 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. And I'll put in the probability of x. We want the biggest values about 0.3, 0.1, 0.2, 0.3, 0.1, 0.2, 0.3. Now the probability of 0 was almost 0.1, 0.086. So let's change the color. Probability of 1 is 0.236, almost 0.24. Probability of 2 is 0.295. That's almost 0.3. Probability 3 is 0.222. We're dropping now. See that? 0.222. Probability 4 is 0.111. Probability 5 is 0.04. Almost 0.05. Probability 6 is 0.01 or 0.01. Very low. You see, now we're going to get ridiculously low values. And I'm just going to put these all along here. They're almost like 0. They're not quite 0, but they're very, very small. See? And I'm just going to I'm not going to join them. I'm just going to draw dashes. That's all I have to do. I don't have to draw a little curve through them. That's it. That's a graph. Notice it's positively skewed, all right? So positively skewed, that will happen when p is less than 0.5. We get a symmetrical curve like the last example, and the closer it is to 0, the more positive skewed. Positive skew, if you just have a look at positively skewed on images of statistics, you'll see the graph not be central tendency. It's like very low and then a very long positive tail like this. So we get a lot of low numbers and not many high numbers. a negative skew would happen for when P is greater than, and we would get like this is a negative skew. We have a long negative and high, very large positive numbers, and this is when P is greater than 0.5, we will get what's called a negatively skewed graph. Please research the difference between positively skewed and negatively skewed. And the last lesson we talked about was when it's equal to 0.5, where it's pretty much symmetrical in the center. And that's the normal distribution, is a symmetrical curve where 0.5, P is 0.5. Okay, I want to finish with just a little bit of revision. And do you remember the mean and standard deviation? NP and NPQ for this distribution. So N was 11, P was 0.2. So we would have an average of 11 times 0.2. We'd get an average of 2.2. And have a look at the highest value here. The average is here, 2.2. And I'll just put 2.2. There's the average. And you see that's like in the position of the peak kind of place. Now the standard deviation is the square root of 11 times 0.2 times 0.8. 11 times 0.2 times 0.8. So you have to be able to do all of these steps 1.33. And that's the standard deviation. See where the average is at 2.2. It's the highest part of the curve as well, just about. All right. This is giving you practice with exercise 14b. Good luck. And we've done this lesson, we've done binomial distribution. We've done where we've got an x, p to the x, q to the n minus x. That's the probability of x equals x. So we've done that. We've done the graph. And we've done a little bit of revision of the mean and standard deviation, NP and square root of NPQ. All right. Good luck.